So coming back, this is the most important relationship in the entire chapter. That's just the personal opinion. The most important topic in chapter 6 by me. Maybe it's not, no one will agree with that, but this is what I consider. Any log equation can be replaced, converted into whatever you want to say, an exponential equation, comma, and vice versa. Any log equation can be replaced, I should just put in there replaced by, or converted into an exponential equation and vice versa. And here comes the relationship. The notation is log base A of x. Log base A of x. Log base A of x equals a number, y, is equivalent to, this is the double equivalency symbol. Meaning from left to right and from right to left. I can start on the right and get the left, I can start on the left and get the right. So careful how we write this. The base raised to this number equals x. A raised to y equals x. We always start with the base, counterclockwise, a raised to y equals x. This, I consider the most important relationship in this chapter. Knowing that I can always write a log equation as an exponential, and I can write any exponential as a log, will help us with everything moving forward in this chapter. And you can say now, wait a minute, you started with this, you didn't finish, you jumped to this. Right, I did, because I need this to explain what happens next in this picture. So for now, we chose an exponential function. We picked 3 x values. We determined the corresponding y values. And now we want to show the mechanism that when we apply the inverse function to these 3 numbers, we recover or get what? 1, 0, and -3 respectively. But I can't show that without presenting the most important relationship or topic in this chapter, or idea in this chapter. Good. So now, one more time the notation. For a general base is log base A of x. For the common log function, the notation is log x. And for the last one, the other special one, for natural log function, is ln x. It comes from German. It should have been natural log and L, but it's ln because it's a German mathematician who came up with it. So then, these are so important again. Let's take a look for a moment. They share the same key with share the same key with 10 to the x. Why do you think these two share the same key? For the same reason why these two share the same key. For the same reason these two share the same key. For the same these two share the same key. For the same reason why these two share the same key. They're inverses of each other. Exactly. So 10 to the x with log means base 10. E to the x with ln means base e. Perfect. So we're coming back. I didn't forget what I'm doing. So here I am. I want us to apply, because the inverse function of this will be ln. We want to apply natural log to e. We want to apply natural log to 1. And we want to apply natural log to 1 over e to the third. Ready? So our f of x, which is f inverse, is natural log e. We want to find a number. F inverse, which is natural log for e, of course. And this is of 1. Natural log 1. And the last one, f inverse, applied to 1 over e to the third, equals natural log of 1 over e to the third. We don't know the properties of log function yet. Yes, please.
Do those cancel out? ln over e.
In a way, because they're inverses of each other. But not in the way I think you're thinking of, maybe. So we don't know the properties of the log function yet, so I would like us to look at the graphing calculator. So in the graphing calculator, let's put in ln. We will learn the properties in a minute. ln e, here is the key for e, where the division symbol is, with the second and e, which is, close the parenthesis, it will work without it, but you know me. And we get, we expecting 1?
Mm-hmm.
Yes, okay, let's put in now natural log of 1. What are we expecting? Careful, what are we expecting? 0. Okay, and the last one, natural log of 1 divided by e to the third. This is e to the third. Close the parenthesis. What are we expecting?
-3.
Good. So then, with this, so this is 1, this is 0, and this is -3. So we concluded that this is indeed the inverse function. The inverse function is indeed natural log x, because when we applied natural log to e, it returned 1. When we applied natural log to 1, it returned 0. And when we applied natural log to 1 over e to the third, indeed, it returned -3. So we will conclude that e to the x and natural log x are, help, of
Each other.
excellent, are inverses of each other. Inverses of each other.
You mean natural log of e or x? Is this e?
Natural log of e is just 1. Natural log of x is the function.
Or the x on the other side? Yeah.
If there is no x, there is no function. If I put here e is just one number. Clear?
Yeah.
Perfect. Okay. I would like us to look at a few properties of the log function. There is no other function that has these properties. Which page am I on? Power. Let's start with product. Product rule. Log in any base of a product is a sum of 2 logs. Log base a of x and log base a of y. This relationship is to be looked at dynamically, meaning I can start with log of a product and I can get the sum, or I can start with the sum and get the log of a product. So it goes both ways. Here's an example for you. Let's say we want log base 7 of 3 times 2. You can say this is log base 7 of 6. True. But it can also be written as log base 7 of 3 plus log base 7 of 2. We will not need to do this. I just gave an example with numbers, but we will need to do this for variables. Next one is the quotient rule. Log base A of a ratio. Can anyone give it a shot? What do you think this equals to? Exactly. Excellent. So this will be a difference. Always from the top minus log of the denominator. Finally, the power rule. Log base A of x raised to a power b. This is the only function that allows us to bring the power in front as a factor, meaning b multiplied by log base A of x. Some other little properties. Log base A of 1, log base A of A, so if this is 5 and this is 5, and this is A and this is 1. Let's say I don't know what this is, but I know how to change this into an exponential equation. A raised to this power is 1. Counterclockwise, we start with the base. A raised to this power is 1. What do you think the power can be? Exactly 0. Let's say, again, I don't know. I have no idea what this is. But I know that A raised to a power is A. What could this be? 1. So log in any base of 1 is 0. Log in any base of the base itself is 1.
So you're saying that's what the log equals?
Mm-hmm. Yep. Log base A of A is 1. Log base 7 of 7 is 1. Natural log of E is 1. Log base 10 of 10 is 1. And log base, any base of 1 is 0. Okay, before we look at some examples, I know I only have 10 minutes left. I would like us to look at the following function. Log base 5 of x squared minus 2x. We're asked to find the domain. What did we say about the log function? Is it a friendly function or not?
Yes. You said that.
It will join the square root, rational, and log, not friendly. Nope. Here's why. Before you say anything, allow me to go back. I cannot apply log to any number other than not 0, 0 to infinity. So log is not a friendly function. If the quantity I apply log to is not strictly greater than 0, we cannot apply log to it. So then, coming back to our function, what would you tell me to write? We have to write something.
Oh, x from 0 to 0 to
X squared minus 2x
It's greater than or equal to zero.
not equal to. One more time. One more time. Not equal to. Because the range of the exponential function doesn't have 0 in it. The domain of the log function cannot have 0 in it. Perfect. Good. So what type of inequality is this? Because you have this on the test on Tuesday. What type of inequality is it and how do I solve it?
Can you do a little chart there?
Correct. Excellent. But what type is it so we can identify it correctly? What is it? Very good. It's a quadratic inequality. Excellent. What do I need to do next? Yes, wonderful. The table, the chart, yes. Yes. Great. What do I factor? Excellent. Awesome. If I don't have a product or a ratio of factors on the left-hand side and 0 on the other, or vice versa, I cannot use the table. Remember, the table only compares signs, not numbers. So this is x is the variable in the problem, x is the first factor, x minus 2 is the next factor, and x minus 2 is what I care about. Not about each and every piece, but I care about the whole thing. I need how many numbers in the table at the top? Exactly 2, 1 for each factor. In ascending order, can you give them to me? So then 0 and 0 and 0 and 0. And since they are linear functions with a positive slope, what will be the sequence of signs? Very good. Excellent. Sign on the first subinterval because I multiply 2 negatives. Excellent. In the middle. Excellent. And the last one. And now I know which sign to pick as the domain of this function. Yes, indeed. The domain of this function is negative infinity to 0, union 2 to infinity, where the expression is positive so that I can apply log to it. Excellent. Great job. I want us to look at few equations. Please feel free. They said 7 through 57 odd. You can choose anything you want. So we want to look at few equations with log. Anything you want. Which one? 31. This one. Perfect. Excellent pick. So 31. 31 is log base 9 of x. They say equals 1/2. Great job. 9. Sorry about that. I have no idea what this means, but I do know that this can be converted into an exponential equation, starting from the base.
9 raised to power 1.
Good, which means x equals the square root of 9, which means x equals. Now, I want to check my answer with the graphing calculator. There is something called the change of base. You may say, this is redundant. My calculator can or allows me to put the base I want. True. It's possible. I have not used a calculator that allows us to put the base that we want to, so we should still know the formula. So if I want to determine log base a of x, and assuming that the calculator allows me just, or has only log and ln, then I have log of x over log of a, or ln x over ln a. Please do not confuse this with a quotient rule. This is a quotient of 2 different logs. The formula is log applied to a ratio, which is a totally different story. So this is log applied to a ratio, which is a difference of logs. But this is log applied to a number over log applied to another number. So let's say I want to determine log base 3 of 9. I'm not going to use any change of base formula because 3 raised to which power is 9? 2, and I'm done. But if you ask me to find log base 3 of 2, I'll say, what? I don't know what I raised 3 to get 2. I know that I raised 3 to the second power to get 9. But I'll stay here forever. I will not be able to come up with an answer. So we're going to use the change of base. It doesn't matter if you use the common log for both, of course, or natural log for both. So let's say we want to use log 2 over log 3. I need the yes, Mike?
So the shortcut to that, you just take the log of the number and divide it by the
Log of the previous base. Yes, exactly. So looking at the graphing calculator, I have log of 2, close the parenthesis, over log of 3, close the parenthesis, and I get whatever, 0.63, approximately. How do I check my answer? Please.
Well, you keep going to math, and then go on the log base, and then type that in.
It's very possible that it has the options. I haven't even checked.
Yes.
We still need to know the change of base formula. Right here, yes, I see it. Yes, so it allows you to do that. So when we go back to 0.6309, how do I check this answer? What does this mean? How do I check? 3 raised to this power should equal 2. So, but of course I'm going to raise 3 to the previous answer, so I don't truncate the number, and I will get 2. If I truncate the number, I will get an approximation.